If a supplier says, "This is a 1000 CFM blower," you still do not know whether it will work in your machine. Airflow without pressure is like speed without a hill. In the next 4 minutes, we will size a centrifugal blower from one real duty point, then check the curve, power, controls, and installation before requesting a quote. Step 1. Define the job, not the fan. Our worked example needs 1000 CFM at 1.5 inches of water gauge. 1000 CFM is about 1700 cubic meters per hour. 1.5 inches of water is about 374 pascals. Write both values together, and state whether the pressure is static or total. Never compare a static pressure requirement with a total pressure curve. Where does that pressure come from? Build a pressure budget. Add the clean filter loss, coil or heat exchanger loss, duct and elbow loss, grill loss, and any process component. Use the resistance at the required flow, not a convenient maximum from a brochure. In this example, the pieces add to 1.5 inches of water. If a filter loads in service, define a second, higher resistance point as well. Step 2. Turn that budget into a system curve. For a fixed air path, pressure loss is approximately proportional to airflow squared. Put the required point on the chart, then draw the system curve back toward zero. The blower will not simply deliver the number printed at free air. It settles where its fan curve intersects the system curve. That intersection is the actual operating point. Now open the performance data for the exact model, speed, voltage, and test configuration. This Longwell GC-B250E-EC-99 example sheet shows a curve from zero pressure toward roughly 2400 cubic meters per hour at free air. Our 1700 cubic meter per hour, 374 pascal target lands near the published curve. That makes the model a plausible preliminary candidate, not an automatic final selection. Confirm the test basis and obtain the precise performance table from the manufacturer. Step 3. Test margin intelligently. Add the loaded filter or worst resistance curve. If the intersection moves beyond the available speed range, the initial selection has no useful reserve. But do not add an arbitrary 20 or 30% everywhere. Oversizing can create excess noise, unstable control, throttling loss, and unnecessary cost. Margin should cover named uncertainties, filter loading, density, manufacturing tolerance, and the expected control range. Step 4. Check power at the duty point. Air power is airflow in cubic meters per second multiplied by pressure in pascals. Here, 0.472 cubic meters per second times 374 pascals is about 176 watts of air power. Electrical input must be higher because the fan, motor, and drive are not perfectly efficient. A datasheet's maximum input power is not the same as input power at your operating point. Ask for duty point input and confirm motor and controller limits. Step 5. Correct the boundary conditions. Fan pressure changes with air density. High temperature or altitude reduces density, so a curve based on standard air may not represent the installed result directly. Also check contamination, humidity, corrosion exposure, duty cycle, inlet distortion, and outlet restrictions. A tight elbow at the inlet or a blocked discharge can move real performance away from a clean laboratory curve. Step 6. Verify the physical and electrical interface. The example sheet lists a 400 by 400 mm frame and about 255 mm depth. Confirm the inlet ring, bolt pattern, cable exit, guards, service clearance, and removal path. The same sheet identifies 115-volt single-phase power plus 0 to 10-volt or PWM speed command and an RS-485 interface. Verify the exact pinout, command scaling, alarm logic, and protection for the ordered variant. Finally, compare sound, not just airflow. Sound data must identify the operating point, measured quantity, test setup, and distance or room condition. Then commission the installed system, measure airflow or a validated proxy, pressure, electrical input, sound, vibration, and control response at design and worst-case conditions. Your quotation package can now be one-page application, one or more airflow pressure points, static or total pressure, air temperature and altitude, voltage and control, noise target, envelope drawing, environment, approvals, quantity, and schedule. Send that package to Longwell and the engineering discussion starts at the operating point, not at a guess.